Good morning, everyone. Today we are going to present our project, a fault-tolerant distributed messaging system built for the distributed system course. Our goal was designing an implementation, a system that can store messages reliably, even if some part of the system fail. We are a team of 4 members, and each of work on a different key components: fault-tolerant, data replication, time synchronization, and consistent using raft algorithm. So each of work on specific key component. The project goal was build a reliable, consistent, and scalable messaging backbone that demonstrates how reliable distributed system maintain high availability and strong data consistency. Traditional synchronous system often have serious weakness. If the main server fails, the entire system goes down. That cause single point of failure. They can also lose data during network problem and scale usage growth. So we wanted to fix the issues, designing distributed system, stay available, consistent and scalable, even someone going wrong. Here's sample views of a system architecture. We have three nodes cluster, a leader, two follows, client connect to leader, send received messages. The leader coordinates with the follows to keep with data sync. Each node include four main components: fault-tolerant, message storage, time synchronization, and draft consistency. Our system, our system written in Python 3.11 using only standard library, no external dependencies. For communication, we use TCP socket which guarantee message delivery. We handle concurrency with threading and Asyncio. So multiple tasks can run efficiently at once. This approach kept our implementation lightweight, fast, easy to test.
So moving on to the first component of our distributed messaging system, it's basically the fault tolerance and failover. So this was done by Atanayaka. So this component ensures that the cluster continues to run even when one or more nodes fail. Health checks are performed through a TCP every second, detecting failures in less than 3 seconds. If the leader node fails, clients are seamlessly transitioned to a new leader without downtime. This was achieved using exponential backoff of reconnections and thread-safe operations. In testing, this component passed all its health and failover tests successfully. Now moving on, our second component is basically the data replication and storage. This was done by Jayatilaka. So this component focuses on data replication and storage. So to achieve this, we implemented draft-based replication where message must be stored by a majority of nodes before being committed. To prevent duplicates, messages are uniquely identified by a timestamp counter, and it supports fast, thread-safe retrieval of messages and can handle up to even 10,000 messages per second with sub-millisecond latency. So moving on to a third component. This is basically time synchronization. So each follower queries the leader's time, measures the round trip delay, and then calculates the clock offset. This offset ensures that all timestamps in the system remain consistent. It is similar to how network time protocol works, but optimized for our cluster. Our implementation achieved an impressive 1 millisecond accuracy, which is crucial for maintaining the correct message order and timeout handling. So finally, draft consensus. So this was created by Hitosh. So this focused on implementing the draft consensus algorithm, the heart of our system's reliability. Raft handles leader election, log replication, and ensures consistency among nodes. It guarantees that only one leader exists per term, and once an entry is committed, it's never lost or overwritten. We use randomized election timers between 500 to 1000 milliseconds and a 150 millisecond heartbeat interval to maintain coordination. So moving on. So moving on to our system integration and communication. all our components communicated to over TCP sockets using unified JSON message protocol. This ensures every node can encrypt messages from others seamlessly. For an example, when a client sends a message, it flows through fault tolerance, message storage, time synchronization, and draft consensus before being committed to the cluster. This integration makes the entire system cohesive and self-sustaining. So moving on, so the testing approach we used. So we took the testing a bit more seriously. We conducted unit testings, integration testings, and even some kind of real world scenario tests. So all our 19 unit tests passed, and our unit test also, I mean, collective integration test also passed, and we achieved 99% accuracy in our tests, and so it was done. So now moving on.
In our demo, we started three nodes, one leader and two followers, and a client sending messages. Then we simulate a leader crash. Within a few seconds, the system detects a failure, elects a new leader, and continues running normally. No data is lost, and the clients reconnect automatically. This live demo clearly shows our system's ability to recover automatically from triggers. We faced several challenges during development. First, race conditions solved using thread-safe logs. Second, network timeout tuning. We adjusted the values through many tests to balance speed and stability. And finally, implementing graph itself was complex, especially handling leader elections and partitions, but careful testing helped us get it right. Our system achieved 99% uptime, zero message loss, strong consistency across all nodes, fast automatic recovery. We also learned a lot. Distributed systems are complex and require careful thinking, timing. Testing is critical to catch subtle issues. Concurrency and synchronization must be planned from the start. Overall, we built a system that's both technically correct and practically reliable. Even though our system already works well, we have plans to improve it further. In the short term, we'll add persistent storage, TLS encryption, and monitoring dashboards. In long term, we'll add read replicas, multi-region replication, and Kubernetes development. To conclude, our project successfully combines theory and practice. We implement Raft, achieved fault tolerance, and proved that it's possible to build a self-healing distributed system using pure Python.
To wrap up, our project, the Fault Tolerant Distributed Messaging System, successfully demonstrated how distributed system principles can be applied to build a reliable and consistent communication platform. We began by addressing the main weakness of centralized architectures, such as single points of failure, data loss, and limited scalability. And we replaced them with a distributed model that ensures continuous availability, data replication, and automatic recovery through the Raft consensus algorithm. Each module contributed to that reliability. So, fault tolerance handled the failure detection and failover. The replication maintained message consistency. The time synchronization aligned all node clocks. And the raft ensured that every node agreed on the same state, even during failures. Our testing confirmed that the system's strength is up to its expectations, which means there's zero data loss, and the recovery is under 3 seconds, and it pretty much met our expectations. So, also, the live demo proved that the client operations remain uninterrupted even when the leader fails. Overall, this project helped us deeply understand the complexity of real world distributed systems, from managing concurrency and timing to achieve consensus. In the future, we plan to extend it with more persistent storage, more determined security,
and a multi-region scalability that can be applied to different sectors. So, in conclusion, our system not only met its technical objectives but also bridged theory and practice, showing that with proper design and coordination, the true fault tolerance is achievable. Thank you.